Now, before we move on, looking at the expected value of, in this case, a discrete random variable, let's remember, keep the big picture here. A random variable has to be a number, and it is quantitative in nature. And then remember back from note set one, if a variable is quantitative, we want to look at various aspects of that data. Remember that when we're looking at quantitative data, we want to look at the four aspects of the data, including the typical value being center or expected. Okay, so that average value, variability, in other words, spread, the shape, and any unusual observations. So we're going to start by looking at that expected value, in other words, that center for a random variable and how we actually find it. We're going to do that via an example. So looking at digital camera components, an electronics store has determined through historical sales data that when it sells a camera, 60% of those customers also purchase an extra memory card, 40% include an optional battery, and 30% of the sales include both. We're going to define the random variable C as the number of additional components purchased by camera buyers. We're going to also assume that if they did buy an extra component, they only bought one. So they only bought like one optional battery or one optional battery and one memory card, extra memory card, but they didn't buy multiples of any of them. So let's start with, is C a discrete random variable? Why or why not? Well, first of all, is it going to vary from customer to customer how many they're going to purchase, how many components? And the answer is yes. Is it the value a number? Yes, so that's looking good. Is it discrete? And the answer is yeah, we can count. What's the smallest number of additional components they could possibly buy? And hopefully you think, well, they don't buy any. True, they buy zero. They could buy one. They could either buy an extra memory card or an optional battery, or they could buy two, which would include both an extra memory card and the battery. So yes, it is quantitative and it's countable. So it is discrete. What is the probability distribution for C? So here is where we want to go back and think about what we've seen so far. And we think, okay, we've got, oops, sorry about that. C is the number of components. And like we just said, you can either sell zero, one additional component, or two additional components. But we want to know what the probability is for each of those to happen. Keeping in mind, what does the total probability have to be a valid probability model? And hopefully you think right away, oh, it has to be one and there can be no negative probabilities. Perfect. So what do we know so far? Well, we know in the problem that 30% of the sales include both an extra memory card and an extra battery. Okay, so that's given to us in the problem description. So now we know that these two together have to total 0.7. And you may be like, well, okay, we got that 60% with an extra memory card, the 40% optional battery. How do I use those? Well, there are a couple of different ways you can do this. You could use the general addition rule, which doesn't naturally come to my mind right away. You could use a Venn diagram. Once again, not my first choice. What you're going to find is I'm going to say, oh, contingency table all the way. So let's do a quick contingency table. I'm going to use MC for shorthand for memory card and B for battery. So let's see, I can buy a memory card or I cannot buy a memory card. I can buy a battery or I cannot buy a battery, additional battery. And we know in this bottom corner here, to be valid, the probabilities have to total, the row across has to total 1 and the last column has to total 1. And what do we know? Well, we know that 30% bought one of each, so they bought both. That's given to us. Perfect. It says 60% of those customers also purchase an extra memory card. Well, they tell us they purchase a memory card, but they don't tell us any information in that relative to the battery. And then 40% buy a battery, an optional battery. Perfect. Now, hopefully you're thinking, oh, wait a minute, this now looks familiar. I can fill this in. Remember, everything has to total to the appropriate number. So I need to put 0.1 here to get to 0.4. This has to be 0.6 because when I add down, I need to get to 1. This has to be 0.4 here because this has to total to 1. And this has to be 0.3. And so forth. This has to also be 0.3. So a lot of 0.3s here. And I'll be very careful when I reference which one I'm using. Now, then to complete this, it says, what's the probability that we buy 0? Well, we've got no battery and no memory card, and that's right here, 0.3. So that's this one right there. Now, do I need to do any further calculation? Well, the only thing I need to do is say, well, I know that this has to add across to 1, this probability distribution, so this has to be 0.4. And I could double check myself there. I could go to the memory card, but no battery, and that's 0.3, plus battery and no memory card is 0.1. Add them together, and you get 0.4. And there you go. Now, expected value. We've already said that's the center. We can't predict exactly how many optional components a consumer, in this example would purchase. It's a random variable. It's going to vary from consumer to consumer. But we can talk about what we expect to happen in the long run over many customers. So the expected value of C is the average number of optional components purchased over a large number of camera buyers. You're going to see E here, that's standing for the expected value of C. So this is expected value of C and this is mu, equals the sum of C times P of C. And you're like, whoa, what's C and what's P of C? Well, this is actually just a weighted average. And you've done weighted averages before, I know. The weights are actually the probabilities. So there's your weights here that C can take for a particular value. Now, the easiest way to do this is actually to show you. Let's start with, we want the expected value for the number of components. Now you have to account for everything that's in this table here, in this probability distribution. So I have probability I buy 0 components is 0.3. Plus, I also can buy 1 component, or the consumer, can buy 1 component. That's 0.4. That's the probability of that happening. And then finally, the probability of them buying 2 components is 0.3. You're going to notice I've accounted for each of my C's, each of the counts, and that the probabilities here, if I added up just the probabilities by themselves, it would total to 1. Now, funnily enough, and this is 0 just so that we're probability of 0 plus 1 times the probability of just 1, just so that you can see this here. This actually works out to be exactly 1. Does that mean that it's a valid probability distribution? No, no, no. This one here is the expected value. So what does this mean, interpretation? In the long run, over many customers, we expect to sell 1 additional component per customer on average. So like what we did earlier. Literally, in the long run, many customers, we expect to sell 1 additional component per customer on average. So this is an aside, an example. What if we had 10,000 customers or consumers? How many of those additional components would we expect to sell? And hopefully you think, well, I expect to sell 1 per customer times 10,000, and that gives me 10,000. Does this mean that it will happen? Absolutely not. Okay, there is no guarantees of this at all. This is just what we expect to happen over the long run. And this is assuming that these probabilities that we're using are that actually reflect what we've seen probably historically. Now, suppose the memory card sells for $5 and a battery sells for $15, and we're going to define R to be the revenue from the sales of the additional components. Develop a probability distribution for R, and hint, we're going to need to look back at what we found in C. So once again, we're doing a probability distribution, R being for revenue, and we need the probability of each of these. So no sale would be the first 1. There's no sale and you make $0. And then you could sell, let's see, in this case, you could sell one memory card, and those are $5. You could sell a battery. I'm just going to do B for battery, and that's $15. Or you could possibly sell both. In this case, you'd get $20, and they're not talking about any bundle discount of any sort. Now, what do my total of my probabilities have to be? And you're going to get sick of me saying this, but it needs to be 1. All right. So now we're interested in no sale, just a memory card, to sell just one battery, and to sell both. Can we get that information from something we've already done? And the answer is yeah, it's right here. So I'm going to circle these using different colors so it can be clear where the things came from. This is the first one. No sale. We know that here's where we sell both, and here's where we sell neither. Okay, so no sale here. This would be the first one. And that probability is 0.3. And we see the probability that we sell both is also 0.3. Those are kind of the easy ones to see. But what about these two here? How about the probability that we sell a memory card, but no battery? Let's see, a memory card, but no battery. That's going to be this 0.3 right here. So we sell a memory card, but no battery. And then finally, we sell a battery, but no memory card. I'll do that in, let's see, not red. How about we do that in purple? And that's going to go here. And we add across and we get 1. So what would the expected revenue over many customers be, and what would the interpretation be? Hopefully you think, well, I'm going to take 0. So I would make, let's see, go back to black here. I'm going to make no money. Probability is 0.3. I'm going to make $5. I'll put little dollar signs just so we're clear here. Probability of 0.3. I make $15. Probability of 0.1. And I make $20. Probability of 0.3. And if I calculate that out, I get $9. So $9 is the expected revenue over many customers. Now you may be saying, well, wait a minute, but $9 isn't any of these. That's true. But remember, we're looking at an average, okay? What we expect over many, many sales. As long as it's in this interval, you're in pretty good shape. What if I had gotten $25 as the answer? It would have been like, oh, wait a minute, crap, there's no 25s even, that's somewhere out here. There's no 25s. So it doesn't matter that it's not one of the exact possible possible values for the random variable. It's okay, but it's in the data set between 0 and 20. So what's an interpretation? So I could say $9 is the expected revenue over many consumers. We expect to make $9 per customer on average in the long run. So there are different ways to say this, but what you really want to focus on is telling me what you're making or what you're doing in terms of we expect, and then in this case, to make whatever the problem or to fill in that part for the problem on average over in the long, and you want to make sure it's like on average, and you also want to get in the long run in there, because remember, this isn't just one time, one thing, one example, and then you have it I should say, not one example, excuse me. I should say just, it's not just one customer, it's over many, many, many customers, over many, many sales. You're also going to notice that I didn't write down those interpretations. This is practicing taking notes. You should be writing down those interpretations.